All right, good morning. I'm always happy to be the early presentation of the morning, so hopefully everybody's awake enough, had enough sleep, not too much partying going on. So I'm Jon Karafin, head of Lightfilled video for Lytro, and I'm very excited to be here and have so much interest in light field capture and the entire ecosystem for Lightfilled. It's something that is truly required in order to enable this to go from an end-to-end production ecosystem all the way through to the consumer. It's not anything that one company can do by itself. So through this presentation, I'm going to show some new content. I'm going to actually show a bit of a deeper dive into the full workflow, the image formats, how Lytro is doing everything from getting the acquisition, how the data servers work, how do we actually record at these types of data rates into the actual image file itself. And obviously at the end, I'm happy to take any questions that you have. Happy to dig even deeper. We only have 20 minutes or so for the presentation, so I will talk very fast. Hopefully not too fast, however. So diving right in, Lytro announced recently, we showed at NAB the new Lytro Cinema technology. We had other announcements for the Lytro Emerge VR technologies. I'm going to be focusing pretty much on the Lytro Cinema because that is where we have the most standardization efforts going on today. And before I get ahead of myself, I really want to dig into how the camera works, because this is really important to understand in terms of how do we look at Lightfilled as a whole, as an entire industry, to go from the capture through to the display, because there's a lot of different types of ways, as Chris was showing, that you can create or conceive of light fields. So first, the core of the underlying technology is something that we call a microlens array. And what you're seeing here in this little video clip is one of such samples. The technology is actually something that we do at the wafer level, and this is where we are able to fabricate extraordinarily accurate microlenses that are, in this example, these are in the order of tens of microns in size, with exacting allocations for how we have the angular distribution for every single ray that goes through this system. On the Lytro Cinema technology, it is much larger because we have an imaging plane that is one of the biggest imagers that I've ever seen personally, and that allows us to achieve the resolution of 755 megapixels. But in this example, you're seeing hundreds of thousands of lenses. In the cinema system, you're seeing many millions of lenses. And then when you take that, it is effectively the exact same thing as having one of these full camera arrays, and you're compressing that into a single sensor and a single lens. So one thing that's really important to understand about the standardization effort here is that there is fundamentally no physics or no computational difference between an array of cameras and one single planoptic camera. You are able to transition between the two systems to go from a true multi-view into a 4D planoptic conversion with no data loss. So that's something that's really interesting and important to understand when you go to how do we have these files, how do we go between these different systems. It is simply just reformatting that data into a different format. So that's something that we like to highlight. I'll go into how you do those types of conversions from a high level. So with this data, the key difference between when you think of the light field display and then you think of the light field capture, we have a main lens in the system. You have to have this main lens in order to converge the rays of light at the image surface, which in this case is the microlens itself, rather than having it be at the sensor. When you have a light field display, obviously this is now your eye. Your eye is actually receiving those rays, and that is how you're able to re-image effectively the entrance pupil of each of the lenses, rather than the microlenses re-imaging the entrance pupil of the main lens in the planoptic system. And from here, when you look at this microscopic view, and I like to make it very clear, this is for exemplary purposes, because I was quoted once as saying I only have 6 pixels and 1 microlens. I don't know why. Anyway, but what happens is you are converging these rays of light from the main lens, and they focus at a position. In this case, it's at the microlens itself, and they break apart into the in-focus rays into those fundamental components, and this is what gives you the 4D function, because now I have a complete understanding of the optical system inside of the camera. I know how to re-project or inverse ray trace all of those rays through the individual microlens, through the main lens, and then back into the real world. And that is fundamentally the 4D planoptic function. So to give you a quick little ray trace of how all this works, I'm going to come around at an angle here. You see that these are just arbitrary points in space. Ignore what it is exactly. It could be anything. You have a main lens, and I've animated this so you can see the effect of changing the entrance pupil size, changing the size of your focal length, and what that does to the rays of light at the microlens plane itself. So again, assume arbitrary object. If you look at how this object is spraying, this is the fundamental UV function here. When you see that this is then filling the entire entrance pupil, it's a really important thing to understand is that you do not have just a ray that hits your image plane. We can then have one ray, fills the entire entrance pupil, converges at one of these particular microlenses. You now have the angular contribution. So the thing that this now forms is a full resolution image at each of these convergence points. This is your array of cameras. There is zero difference between doing this and having an array outside of the fact that this is an extraordinarily dense array of cameras that you can now compress into one single main lens. And the advantage of doing this now is you don't have to do any lens-to-lens calibrations. You don't have to worry about sensor-to-sensor calibrations. You have one entire system that allows you to capture the holographic image and reproject that back into space, depending on where you have your desired focus. So, what does this give you? How do we take these images? How do you compute these images? And how do you convert this from the 4D function back into that multi-view image or the array of images? So the easiest way to think of this is, now imagine you're standing behind the sensor and you're looking through that main lens, kind of an awkward position. We divide the main lens into what we call sub-apertures. And these sub-apertures are effectively these little pinholes, and you can think of them as an even distribution of apertures within the main lens. And obviously they don't look like these little icons here. And if you were to take now the top left pixel behind each of the microlenses and then form an image that converges right here at this top left, and you are imaging this object here, you now form one full resolution perspective, or your top left camera array, because you're resampling and stacking up all those pixels from that top left coordinate. And similarly, now if I sample that bottom left, or I sample the top right, you form all of your multi-view images. Right? So this is how you can now transfer between the many different types of systems, and you still maintain the full 4D function of light field data. Now, this is a very naive approach of how you actually do the image processing. You're actually sampling many hundreds of pixels for every single pixel in order to have super resolution and a lot of other things that you do for the final output image quality. But this is the fundamental concept of how you could think of this type of image. So from here, we'd like to just show that this is somebody's little boat that their kid made at work and put it outside in a rainstorm. But this is the 4D image. Looks like when you just see it on the screen, this is kind of blown up, this little subsection, but it's a fly's eye view of the world. And again, when you take these coordinates and you have an exacting understanding for every single ray, every single UV coordinate for every single microlens, this gives you the full understanding of how you have the holographic data. And you can then reformat that image for any particular type of display. Alongside of that, we now have the XYZ data per pixel, meaning I know how to project every pixel, every coordinate into the real world to reform my image. And this is the inverse ray tracing that gives you that final 2D output, or how you could then reformat your content for any of these such displays. So this is really how we like to think about light field cinematography. It's now capturing the image data as if you have a full hologram of the world, and this is actually a point projection that comes off of the Lytro Cinema system. So now you have not only the color and the intensity of the data, but you now also have the XYZ coordinate for every pixel. And depending on where you select what pixels you want to then ray trace into the scene, you're then getting that full volumetric data. Now, as this highlights, because we are shooting from one main optical element, that defines your point of view and your parallax. That defines how far you can move a virtual camera truly optically correct. But depending on your scene, you can then have a new virtual camera. You can move around it. You just have now occlusion data with none of the 4D data. So that is really how to think of it. If I had a lens that was the size of the room, then you could then move your parallax the entire size of the room. That's the easiest way to go between these many systems. We like to think of the technology of all light field technologies as the future of imaging, as the next industry standard for how we should capture, how we should display all content. As Chris highlighted, it really is the thing that gets us to recreate reality. And we very strongly believe that these types of standardization efforts are truly required to make this something that becomes an industry standard. And as we go forward, we're happy to collaborate, to share image files, to share the metadata streams. I'll go into that in a moment. But for the Lytro Cinema technology, it's not just a camera, it's an entire ecosystem. It's something that's really important to understand, because when you have a traditional cinema camera, you have the camera, you have your data, and the camera is then out of the picture for the rest of post-production. For a light field technology, it's not only now the camera, but now you have all the server architectures. We also provide a cloud ecosystem. We also provide all of the editing tools. So you have to go from end to end through post-production into now the distribution output options. Depending on what the format is, you can then optimize this to be something that is truly the highest possible quality depending on the display that you're targeting. So I'm going to show a very quick little piece. Some of you may have seen this. This is the recap of the technology. We have David Stump and Robert Stromberg, who are the first to use Lytro Cinema. We released a short piece of film at NAB, and this is a bit of the behind the scenes, and you'll unfortunately see me talking on it too, but again, you got the real one here, or the one that's recorded. So it's a very quick piece. This gives you a recap of the technology, and then we'll dig into the actual image files and formats.
As a visual effects artist and supervisor, I've always been curious about what's next. It sometimes feels that visual effects can sort of slow things down. I think we're now at a point where you can not interrupt the flow of work and keep the creative direction constant.
If you get me more coverage, I'm able to make the movie you want me to make today. If you only just shoot it in one way, I'm locked in.
What is exciting for me about this camera is that it is headed down a path in imaging that I've always wondered whether it was possible or not. This is proof that it is possible.
Video until now has been a 2D medium, and computer graphics tend to be three-dimensional. Cinematographers and visual effects artists are doing amazing things, but they have to struggle through the fact that these are two different mediums. What Lightfilled allows you to do is that it integrates the two worlds. It turns every frame in a video into a three-dimensional model.
Lightfilled cinematography is the ability to capture everything about a scene, from different perspectives, different focal planes, and different apertures. Every pixel now has color properties, directional properties, as well as exact placement in 3D space. Essentially, we have a virtual camera that can be controlled in post-production.
Lytro Cinema offers the ability to focus anywhere in your scene. You have the infinite ability to focus and create any aperture or any depth of field. You can shift your camera to the left, you can shift it to the right, as if you had made that exact decision on set, and you can even move your camera in and out. Automated camera tracking removes that tedious task of integration and matchment. It has all of the volume, all of that depth information that easily allows you to composite and matte your CG objects. With depth screen, it's as if you had a green screen for every object. But it's not just limited to any one object, it's anywhere in space. When you capture in the high bandwidth mode of Lytro Cinema, it gives you the ability to then reconstruct any shutter angle and any frame rate. So this allows you to use motion blur as a creative tool rather than something that's baked in at the time of capturing.
Lytro Cinema is the highest resolution video sensor ever designed. Every frame has 755 raw megapixels, 16 stops of dynamic range, and we can record at up to 300 frames per second.
Lightfilled Cinema includes a high-resolution active scanning system. The complete system provides a powerful server for storage and processing, which can also be done in the cloud. We've designed the system to integrate directly into existing pipelines to allow artists to use plugins to edit the Lightfilled data.
Lytro Cinema is an entire ecosystem. Standard visual effects, which were very difficult before, come naturally with Lightfilled video.
We're at a point that we can bring Lightfilled technology to the world's most creative people and allow them to realize their vision in ways they could never have imagined.
Lytro came along and said, we can actually do this with technology. We can build a different kind of sensor and modernize that world.
when you have the ability to never miss focus and the ability to change your relative position, and you can do that with a push of a button, you always get the shot that you want. All right, the magic of editing. It makes me sound like I know what I'm talking about. Okay, so I'm going to show something that I haven't shown really publicly yet, so you'll be the first, and you tell me how this works, and I'll revise my slides for the next time. But we're going to dig a little bit deeper into the full workflow and the pipeline. So hopefully it'll become clear that this is a very complex initiative. This is something that takes a lot of collaboration in order to make happen, because you have to go from the camera all the way through to the final rendered output, and there's a lot of steps to get you there. So there's a lot of slides here, so hang with me for just a second. So we start off here, you have the Lytro Cinema camera. Now, in order to make sure that you have the same experience that you would have from a traditional standpoint with a regular cinema camera, we want to make sure you have a real-time preview of everything that you're seeing. So, in order to achieve that, you have the actual GUI, of course. You also have now a focus puller monitor, you've got your reference monitor, we have a whole bunch of other taps and outputs in any number of different formats if you want to do SDI, DVI, HDMI, whatever you want. And everything is on a wireless control system. So this allows you to, we get a lot of questions of why would you have focus controllers? Well, if you want to then preview what your rack focus looks like, you have your focus controller, you give it to your the standard production team. There's no difference, there's no change in what the production team is or what they will do outside of now having a different camera. So you actually now have two focus controllers, blowing people's brains up. What this gives you the control over is the Lightfilled volume focus, because every Lightfilled shot you have a predetermined far point and near point, and we give you the real-time visualization of that. You now have your preview focus control to allow you to then have your focus pullers do their rack focus, anything that they want to do to see the shot in real time, as well as a dynamic depth of field control. So this is giving you the ability to see shallow depth of field, narrow depth of field, anything that you want to do from wide depth of field. You can simulate any aperture doing this at real time during capture. This is then stored as a ProRes or MXF file, depending on what your production needs are, and this is rendered in real time. So you can then get that file, it can go to nearline, go to editorial, you can start your editorial process with that proxy file immediately, but this isn't baking anything in. This is just a metadata stream with the baked in QuickTime files. So the metadata is then going through all of production. The metadata includes what focus decisions were made on set, what color decisions were made on set, what lenses were used, really every single thing that is required to have a full understanding of the holographic scene. But from here, you also now have, when you load the software for the first time, those decisions that you made on set are the very first things that you see in software. And that's really important because we want to have the directors and the cinematographers have full control over their scene, over the content, and not feel like that this is some kind of an arbitrary decision or some kind of crazy new technology that they have lost all control over. Obviously, we need to support all other image technologies. Lytro Cinema, as it stands today, is not the capture system you would use on every single shot, even though if you ask me to do it, no problem. You can use it on every shot. But we look at it more as a new tool to give you a type of capture that gives you different types of effects or different things that you previously could not do with any other technology. So to support that, you obviously now have your Genlock sync. We have all the SMPTE standards that are baked in so that you can give us a sync signal. It will tap directly and allow you to have the same workflow and integrate with other existing cameras on set. So going from here, everything goes to the DIT cart. So that includes either the actual files or the live data stream itself. And you are able to have, obviously, all of the color grading. And this is, at the customer request, able to be embedded directly into the Lightfilled file. So when you project your rays for the first time, that is the actual color that you'll see right after capturing the data itself. The thing that makes now a bit of a unique workflow is the cloud transfer. Lightfilled data is big. Everybody here probably understands that, and that's why we have these standardization efforts. With the full bandwidth at 300 frames per second, the capture system is streaming the data to the servers at 300 gigabytes of data per second, just to give you an order of some magnitude. So we can do that today. That is something we're able to both stream the data 300 gigabytes per second, or we can stream it out, should there be a Lightfilled display that could do that kind of a data rate. in that kind of a resolution. But this is not going to be something that you want to transfer from every single studio. So this is where you get into the more complex workflow of now needing to have some kind of a mechanism to make that data remote. So we're building a cloud architecture, and we have a collaboration with both the Foundry and with Google that allows us to have these POP locations. We transfer all the data on a daily basis. We provide all the servers, all the redundant data, all the data backups goes to the cloud, and now you have something that's kind of similar to a remote desktop system, although very low latency, and what it gives you the ability to do is have all of the software, every single thing that you need in order to perform the Lightfilled modification or all the visual effects on the cloud using just a monitor, a keyboard, and a mouse. And that gives you the ability to have all of your artists worldwide, so every single vendor with all the secure permissions and everything is a direct fiber link, you are able to then have them work on the data without them actually ever noticing how much data they're working with. It becomes something that is a completely remote and cloud-based ecosystem and architecture. From here, we also have all of the EXR files. We have standardized on open source. All the metadata is embedded. Everything is in a linear format. We can also provide the ACES IDT, depending on what the production requirements are. That's just an additional field for the metadata that we can tag in. And then going through the rest of production, everything is in that cloud ecosystem. All the plugins are available should you want to have that on a local architecture. Of course, you can do that. Now you have to have that ecosystem at your local facility and then replicate it through all of the other subcontract vendors. Today we support everything integrated directly as plugins to Nuke and Nuke X, as well as Nuke Studio for some of the editorial, but we can ingest the EDLs from Avid or any other editorial program, and you can perform all the visual effects using the Nuke ecosystem. Eventually we will branch into other applications, including all the editorial and DI. Today we want to make sure we get it right, integrating with that one system, and that's generally where the requests are coming for our customers. And then for post-production, you go into different proxy formats depending on what stage of post you are in. For visual effects, you get the full raw data, and then you also get the 2D proxies, and then depending on what you're doing, you have now a standard ecosystem and a standard format for DI. Nothing really changes there. You get the render files, you can get all the depth information, all the XYZ information should you need that, as well as the editorial process. So I know I went through that really quickly because I'm kind of really out of time here. Happy to go into that offline as well. This is Lytro Cinema. This is the camera. It is a big camera. So we like to not hide that, but at 755 megapixels in order to handle the data rates of 300 gigabytes per second, this is the bleeding edge, state-of-the-art of what can possibly be done today with silicon technology. We are simultaneously working towards the miniaturization of this and making it into a truly handheld system, and that is on the near-term horizon for our development efforts. I like to just show some of the UI, and this is one of my engineers, and I apologize to him every time I show this. So you do have an interface that gives you the full three-dimensional real-time functionality to move around, real-time samples. This is actually the V1. The V2 that's already out is 10 times more dense in real time for all the active samples. You see that it overscans the image from a volumetric standpoint. We have the dense imaging data at the convergence point here, and we have a sparse ground truth scan at real time, at video rates, to give you a real world XYZ coordinate for every single pixel within that sparse sample. But this is all the things that you can do. So you have the different volumetric methodologies to see how to work with, capture, and optimize all of the imaging data. As I mentioned, we had the collaboration with both Google and the Foundry to enable this cloud architecture, and Google has a lot of resources, so they're kind of a great partner to be working with, and they really want to see how they can take that data, and you can probably think of the types of things that they would be doing for Lightfilled as well. And really quickly, I know I'm pushing my limits here on time, but I'd like to just show at least one example of, let's see where my mouse pointer here, what you can do with the Lightfilled imagery. I'm going to show you kind of a kitchen sink example for some of the visual effects that we have enabled through all the plugins. So this is a final shot that was in that piece that we showed at NAB. Might look like a relatively simple composite, but it is actually a very wide stack up of lots of different assets. You have multiple plates that were captured with the Lytro Cinema system. So this is an individual take for the couple. This is a set extension of a virtual plane The silhouette that you see here was a different 4D captured asset. You have a two-dimensional hand-painted matte painting that was done by Robert himself, and then everything is integrated into the final composite. But the way that we did this, just to kind of highlight it here, is this is the original plate. So I always like to show this on the top left, and you do not want to capture like this whatsoever. So this was done intentionally. We let the grips walk behind, and this is how we captured so that you could see the depth screen technology where you're able to extract foreground and background. You don't have to worry about having a truly virtual production set. Because we have all the volumetric data, we can extract foreground, we can extract background as if you had that actual green screen at the time of capture. And this is showing you the visualization of how the automated camera tracking works, that because we have the sparse ground truth data, because we have that dense light field data, you're able to look around objects. We're able to have all of the information of how the camera moved through the real world environment, and we're within a millimeter of accuracy of the true real world coordinate of the camera move. And that happens really just as a byproduct and stored as metadata as well. So going beyond that, we had this as a real take. This is real confetti that you're seeing here. And of course, it's reflective Mylar pieces, which is not what you should ever do, but thank you to Robert for that. But what happened was this is a confetti bomb, which I didn't know is very loud, and it startled the talent. So what the director wanted to do was take the live action confetti from the first take and composite it over a second take where he had the better performance. But they're two completely different camera moves, and you have things that are very, very reflective without any green screens, obviously with the grips walking behind. But using the depth screen, we can isolate that plane in space. We know all of the edge detail. We know RGBA for every single pixel, and we can then plop that right on your second take. That is live action confetti, and then put that into the scene. There is also the ability to automate the rotoscope process. So with the light field data, and I like to show with the confetti, you can see little red dots that pop up. The little red dots show you when it has to resample for everything behind for occlusion, but it gives you a completely locked-in track around every single plane, every object. So this is something that we really like to highlight as one of the benefits for using the light field capture. On this particular scene, you would use it for the feet because the feet are touching a ground plane. You need to segment from the ground plane or put in a synthetic object underneath of them for the set extension. And then as we go into the final composite with all these elements, you use your depth screen, you do the contour tracking. Now I have all the track cameras you project into XYZ real coordinate space. Everything then is based upon one virtual coordinate to allow you to integrate these even though you have all the varied camera moves. So this is something that is now becoming relatively easy for an artist to do in a day versus something that would have taken previously many, many weeks, maybe months, arguably. Okay, and then here you go with the final composite with everything in the final scene. And just to show how, real quick, I'm not even going to show much here, but just show that it's operating inside of the plugin architecture. You can see here how we're able to use all of the tools. You've got all the metadata that's exposed and embedded, and allows all the artists to modify and manipulate all of the imaging data in an interactive environment. Okay. Future, we're working towards miniaturizing this technology, but until we have the pipeline, the workflow, the standardization right, we don't know how to build it to support all of the needs of the industry. But what we do know is that it needs to be handheld, it needs to be portable, so that effort is happening now in order to make the actual resolution and the data rates that you see today something that can be put into a form factor that is much more commensurate with what you see in traditional cinema cameras. We are currently working towards a system that is even higher resolution, even higher data rates, and in a portable form factor. So that is something we're really excited about, but we know that that is the next generation of what to do, and with the entire industry's help, we can make this the right camera in order to capture this data. So I've totally overrun my time, but we have a couple minutes, I think, for some Q&A. I'd love to field any questions that you may have. Yes?
Do you see any applications in the broadcast?
Sure. So the question is, do we see application for the broadcast community? And the short answer is yes, see caveat note. Lightfilled is all about the post manipulation of the imaging data. But you can then stream a live view from the Lightfilled data and go back to it afterwards. So a good example is if you have a sporting event, you want to capture something at these extremely high frame rates at this type of resolution. You're only at real time showing one particular set of decisions. But then if you do an instant replay, you can go back in, you can manipulate the camera data, you can then virtually change your perspective. The downside is you need massive compute power to do that at the types of broadcast requirements. That is just a amount of time in order to get to that. That is something that would have to be focused on. We know how to do these things in real time should we need to. That's just a very expensive development effort to get that kind of compute power. Yes? Thank you. Yeah.
Should we include preview, in other words, flat 2D output, in the mission of the consortium? Does, they call it metrology, I call it rotoscoping. It should be standardized, right?
I would agree with you. I mean, so the 2D, so is your question specific to, should we include 2D as a requirement and spec or as a creative decision that you're matching to? Just to make sure I'm answering correctly.
The eventual open standards should encompass everything we need to make a flat output.
Yes, yeah, totally agree with you. So we should have backward support for everything. It shouldn't be something that, we don't even, I don't think we should, as a community, think of Lightfilled as some exclusive community. It should be something that embraces 2D technology, stereo technology, Lightfilled technology, and the future of what we don't know is that next generation technology. The downside for Lytro right now is we don't have a compelling Lightfilled display to show all that data, so we just throw it away, unfortunately, after you bake it in. Obviously, you have the raw data, but you bake it down to a 2D or a set of multiple viewpoints. So yes, totally agree that it should be part of that open standard to ensure that you have maintained the backwards compatibility for any format moving forward.
Thank you.
Okay.
If I understand correctly, parallax is limited to the size of the main lens.
Yeah, the size of the entrance pupil of the main lens, that is correct. So if you have a really big piece of glass.
So can you explain a little bit more about the streaming structure and going up to the cloud with your 300 frame rates? Tell me how you structure that one, and then when you're streaming downstream to the edit suite, how is that data structured?
Great question. Thank you. This is a whole almost masterclass, but I'll try to do this in a minute. Yeah. So what we do in production today is we have the entire camera heads on a back-end tether. It's a 100-meter tether, and we have a mobile data center that actually has all the HVAC cooling and everything to support the whatever amount of data collection you need. That is what allows you to get to the 300 gigabytes of data per second, should you record at that data rate. But what we then have is a dual redundant storage architecture so that we take the actual drives and we move it to the POP site or the big data hub, and that uploads overnight and we'll do all the pre-processing so that first thing in the morning you can do all of your dailies. But the next day on set, you have your second redundant server. That is what you're doing all your data collection on, and then we do a swap between the two. So that way you always have a redundant backup. You do all your checksums on the cloud. You make sure that everything has all the data validation. You have an artist go through and look at all the content as a triple check. If you want to go to LTO tape, we'll talk offline. Okay. I get that request a lot.
But are you up streaming 40 JPEG streams up to the cloud?
Oh, so
how do you actually
yeah. So all the data is on this local data architecture until that data upload occurs at the POP site. Once we get to the POP site, we have, depending on the region, between a 10 and a 50 gigabit connection. Yeah. So you're not at real-time rates, not even close. Sure. But we will ensure that whatever that transfer time is based upon the production needs for dailies, either the next day or whatever set of days that is required. So it's not a set of JPEGs, it's actually a raw bit stream, and that's how we get to the highest possible compression efficiencies and data rate efficiencies. And then once it's on the cloud, you pre-process it, standardize it into the OpenEXR format. And that's what the actual customers and artists will interact with. And we chose that as a standard because that is one of the most popular open standards for all visual effects. We can embed all the metadata, we can support really the full 16 float, or 32 if you want 32 file formats. And we can have that with our Lightfilled compression, and it's really a very light compression, but it gives us that much more efficiency for the full 16 float data. And then from there, on the way back down, it's a 10 to 50 megabit connection is all you need. And it's because you're just streaming the 8-bit UI. When you want to do more of an official review of the shot, we also provide an SDI caching mechanism inside of the local machines. So that way you can get to the full 12-bit or whatever bit depth that you want resolution for output, and it's basically a pre-cache mechanism to get the full data resolution should you need that beyond what the UI is showing you. So it's giving you basically the best of both worlds. You're only pulling down whatever data you need locally, and otherwise all of the big EXR files stay completely on the cloud. And then you have, obviously, this administrative mechanism to make sure that only people that have the direct connections and have the appropriate permissions can see the data.
Okay, okay.
And I could go on for hours about that.
Well,
Yeah,
yes.
and I don't have that time, but, okay. Moving on, any other questions? I'll be on the panel
Actually, I
afterwards.
have just one, yeah, Tommy, go ahead.
Is it easy or difficult to transform the Lightfilled data to mesh and texture data?
So that's a very interesting question, because one of the misnomers about converting into this mesh data is you have fundamentally thrown out the Lightfilled. Right? When you think about it, if you now have mapped a single UV texture, and this is between VR when you map to a spherical surface, or this is for models when you map a UV texture to the model, what you have done is you've simplified and effectively warped your entrance pupil into one perspective point. So that's just kind of a big caveat that as soon as you go to geometry, as soon as you go to vectors, as soon as you go into something where you only have one image texture, your light field is destroyed. It's gone. And then you have to re-simulate that with understanding material properties and then using a virtual engine in order to reconstruct the light field data. And that is a non-trivial process. Same problem. So it's the same problem. As soon as you go to a single model, unless you are reprojecting your data onto the model, and you're taking your multi-view, and then as soon as you go between viewpoints, you're reprojecting all of that, your model no longer has light field. That's just a thing for us to all wrap our heads around. It doesn't mean you don't have depth, it just means that you don't have light field. So if you move your virtual viewpoints, you don't have the reflections, the refractions, and the things that make it, in fact, a unique light field experience. So moving beyond that point, there's many academic white papers about taking Z data from the camera extrinsics and intrinsics and mapping that onto a mesh. And there's a lot of different ways. Microsoft's done some pretty amazing work for all the HoloLens work that they're doing. So we give the XYZ point pass, which means you have a dense point cloud, and then from that you can do any meshing techniques that you want. So that is a very simple process because we give you that metadata. That makes sense? Mapping, UVs, no light field. Okay. And you had another question?
Well, yes, very, very quickly.
Yeah.
Are you doing any productions right now that you can tell us about?
Oh, boy, you put me on the spot. Due to NDAs, my attorney over here says I can't say anything. So right now we are in that process of, we have many partnerships, and as everybody in this space knows, that before any new disruptive technology goes onto set, you have to go through a whole series of, let's call it studio testing. So all of that is what is happening previously into now, and any production that we may or may not be doing, you will know about when the film is released, which there are very long production cycles, unfortunately. So there's a lot of people we're working with, that's what I can say. There's a lot of excitement over the technology, and we want to make sure we get it right, because in the cinema space, you don't want to release something that doesn't make your customer happy. That's just not something we want to do. But we have a lot of exciting things going on. I can say that. Okay.
Okay. Thank you, John.
Thank you. Sorry for overrunning my time.
Yes.